9. Natural forced convection. Let's get started with natural convection. When we talk about convection, there are two main players, forced and natural. Forced convection happens when we use a pump or fan to move the fluid. But natural convection? It happens all on its own, driven by temperature differences that cause density changes and buoyancy forces. In this session, you'll see how heat can move without any mechanical help. You'll learn where natural convection shows up in real life, from radiators heating your home to the cool breeze by the ocean. We'll also explore how natural and forced convection can interact, sometimes helping each other and sometimes competing. So, think of this chapter as your guide to understanding the quiet but powerful movement of fluids driven by nature itself.
1. Learning outcome. Let's start with what you'll take away from this session. A good learning outcome focuses on clarity and purpose. Every point should show exactly what skill you'll gain or concept you'll understand by the end of the lecture. For example, instead of vague goals like know about natural convection, we'll focus on targeted outcomes like explaining the physical mechanism of natural convection, applying governing equations, and using the Grashof number to characterize flows. You'll also compute Nusselt numbers for different geometries, study real-world applications like heat transfer from fins and inside enclosures, and learn how natural and forced convection can combine in practical systems. Keep your learning outcomes sharp, action-oriented, and connected to practical skills, so you always know exactly why you're learning something.
2. Introduction to natural convection. Let's start with a clear introduction to natural convection. A good introduction avoids filler words and focuses on what's unique about the concept. For example, instead of vaguely saying, natural convection is when heat moves, we highlight what really matters, fluid motion driven by buoyancy effects, without any external devices like fans or pumps. We also keep it practical by adding common examples like cooling of electronic devices, heating systems like radiators, and energy losses through windows. When you introduce a concept, focus on what makes it distinctive and relevant. This keeps your slides purposeful and easy to remember.
3. Physical mechanism of natural convection. Let's start with the physical mechanism of natural convection. The key is to highlight the natural movement of fluids driven by buoyancy, not external forces like pumps or fans. A simple way to make it dynamic is by focusing on the process. Heating reduces fluid density, lighter fluid rises, and cooler fluid sinks, creating circulation. This is the heart of natural convection. Tie it to something relatable. Archimedes' principle explains how ships float and hot air balloons rise. Use these analogies to keep your message clear and memorable. Focus on action. Highlight the why behind the movement. This makes your explanation sharper and easier to follow. 4. Governing equations and the Grashof number. Let's break down the governing equations by keeping it direct and practical. Instead of overwhelming the audience with long equations, focus on the takeaway. Buoyancy forces are added to momentum equations to capture natural convection behavior. Next, simplify the Grashof number by linking it to something familiar. It's just like Reynolds number, but for natural convection. Grashof tells you who's winning, conduction or buoyancy. Small gr means conduction dominates. Large gr means buoyancy takes over. Rayleigh number sharpens the picture by combining Grashof and Prandtl numbers, letting us quickly classify flow as laminar or turbulent. Keep your message sharp. Focus on meaning, not just math. That's what makes it stick.
5. Natural convection over surfaces. Let's make sense of how natural convection behaves over surfaces. Instead of overwhelming with complicated formulas, focus on key patterns. For flat plates, the Nusselt number is linked to the Rayleigh number using simple power laws. Laminar flow uses a quarter power rule, and turbulent flow follows a third power rule. You only need to spot the Rayleigh range to decide which equation to use. Inclined plates follow similar logic, but you adjust for the angle using cosine terms. This keeps your calculations practical for sloped surfaces. For cylinders and spheres, we use more advanced correlations, but the message is the same. Simple formulas make complex flows predictable. Trim the math clutter, focus on trends, and show how quick estimates help in real design work.
6. Natural convection from thin surfaces. Let's simplify how to design effective heat sinks. When electronics heat up, natural convection takes over. No fans, no pumps, just air moving on its own. But there's a trick. Thin spacing matters. Too close, airflow gets blocked. Too wide, you lose surface area. That's why we use the optimal fin spacing formula. It finds the sweet spot where heat escapes fastest. Then, we estimate total heat transfer by accounting for how many fins, their length, and temperature difference. It's all about making small design tweaks that lead to big gains in performance. Cut through the complicated formulas. Focus on smart design choices that deliver better cooling with less effort. 7. Natural convection inside enclosures. Let's rethink how you approach natural convection in enclosures. Orientation matters more than you think. When the hot plate is at the top, you get zero convection, just pure conduction, because hot air can't rise. But flip it, and the bottom plate starts a buoyancy-driven flow once Ra exceeds 1708. This is where simple formulas help. Instead of complicated simulations, you can predict heat transfer with straightforward correlations, just by knowing if your enclosure is vertical or horizontal. Don't waste time on trial-and-error designs. Use the physics of buoyancy to make your enclosure smarter and more efficient. 8. Combined natural and forced convection. Let's talk about when natural and forced convection combine. You can't separate them completely. Natural convection is always present, even when you have a fan or pump driving the flow. The key is knowing which one dominates. Instead of guessing, use a simple criterion: Grashof over Reynolds squared. If it's less than 0.1, forced convection wins. If it's greater than 10, natural convection takes over. Anything in between means mixed convection. You'll need to account for both effects. You can easily quantify this with a combined Nusselt number formula. Just remember, use plus for assisting flow and minus for opposing flow. This small tweak keeps your analysis accurate and efficient. 9. Engineering applications. Let's end with how natural convection shows up in real engineering systems. You see it everywhere, from cooling of electronic devices to the chimney effect in building ventilation. Natural convection even drives better insulation designs and improves heat exchanger efficiency without extra energy input. In each case, you're getting heat transfer without the added cost of fans or pumps. That's why engineers love natural convection. It's free, passive, and always working in the background. When you design with it in mind, you can save energy, cut costs, and improve system reliability. Simple principles, real-world impact. 10. Summary. Let's wrap things up with a clear takeaway. Natural convection is driven by density differences without needing pumps or fans. You've learned how Grashof and Rayleigh numbers guide us in predicting flow behavior. We also explored how Nusselt correlations adapt to different surfaces. In engineering, natural convection shows up in insulation, electronics cooling, and even power systems. But when forced convection is present, you can't ignore it. Always check the GR over RE squared ratio to see which mode dominates. Understanding this balance helps you design more efficient and effective thermal systems.